Hello, this is Francesco Caravelli, and I'm a staff scientist in Los Alamos, and today I would like to talk about locality or centrality measures on networks. This work is in collaboration with Fabio Caccioli and Silvia Bartolucci from University College London and Pierpaolo Vivo from King's College London. This is the perfect conference to talk about this subject because I'm pretty sure all of you are acquainted with the concept of centrality measure. But just to say a few words, in the 60s, Katz introduced the notion of centrality measure for the necessity of finding who was the most central person in a network of social interactions. And if M is the matrix that determines who befriends whom, so this directed graph, you can multiply it by a constant alpha and then invert the identity minus alpha M. And typically, this is one form of centrality measure. The type of centrality measures that I would like to discuss in this talk are of the recursive kind, in the sense that the metric or centrality on the node is in a sense a constant plus a sort of average over the neighborhoods of that particular node. An example is given by the notion of trophic level in a food web or ecosystem in which you're asking yourself who's the apex predator in the ecosystem, and essentially, this is recursively defined linearly in terms of the notion of trophic level. And Aij here is the matrix of energy flow between species. And in fact, this is even more general in the sense that across several fields in complex networks, you see similar quantities defined. In LNTF, input-output economics, you have the notion of Leontief inverses. In random walks, mean first passage times are defined recursively in a similar way. And of course, in computer science and web pages, you have the so-called page rank orders. Across all these fields, the central quantity is given by the following vector, which is defined in terms of a matrix inverse here in terms of A. And this is a nice interpretation that shows why this quantity is non-local in nature. In fact, if you perform a Taylor expansion, we see that every single term in this expansion can be interpreted as k-steps on the graph. Essentially, you see that this quantity is non-local. The key issue is then evaluating this inverse, which does not come from free. In fact, there are some difficulties. The first is the fact that matrix inversion is a numerically intensive process as it scales like n cubed with the size of the matrix n. The second issue is the fact that the network itself might not be known or known partially because there is lack of reliable data or there are sometimes some privacy issues. The same issues clearly apply also in the case in which instead of having some resolvent like centralities, you do have some other matrix functions, such say the matrix exponential. And last but not least, sometimes you do see that there is a strong correlation between these type of rankings that are non-local, as I just said, and some local quantities such as the node degree, for instance. And in order to see this last point, what we can do is to generate some random graphs as seeds of our procedure and evaluate the centrality measures, say the Katz centrality, after we have applied some local graph moves, such as the Maslov-Sneppen dynamics that does not change locally the degree. And what we see is that for not so dense networks already at p is equal to 0.2, where p is the probability of having an edge or not, essentially, there is no change on average on the centrality after all these steps are implemented. And here the y-axis is the average over all seeds and all dynamical moves. It follows that these graph measures are in a way local for dense graphs, and one need to explain why. Then can we provide an answer to all these issues in one shot? For this purpose, let me introduce a matrix A, which is positive and row substochastic, and Zi's are the row sums to the matrix A. One simple example of this type of matrices is the following matrix here, which has the rows equal to Zi's divided by n. Ranking for this matrix can be evaluated analytically via the Sherman-Morrison formula. And what we see is that the Lth value of this ranking is given by 1 plus ZL divided by 1 minus Z bar, where Z bar is the average over the Z. And what we are proven is that, in fact, this ranking here is much more general and is robust in a sense that I'll see we'll see in a second. But essentially, if A is substochastic and non-negative, this is a good approximation for the ranking given by the matrix, provided that ZL is the row sum of the matrix you want to invert. And the way essentially this was derived, let's introduce two types of rankings. One is directly connected to A and one to the A transpose. And we assume that A is positive in the sense that every single element is non-negative, and a row of A, which is a spectral radius, is less than 1. Then what we introduce is a matrix ensemble peaked on the flat matrix introduced in the example. And what we have shown is that under some conditions I'll get into the next slides, the two matrix L and L hat, or the two rankings, are flat in one case, one depends only on Z bar, and essentially the one proportional to ZL introduced before. And what we've been able to do was also to characterize the fluctuations. The way this result was derived was essentially using techniques of random matrix theory. And for those interested, the steps were the following. We first introduce a matrix B that contains both I minus A and I minus A transpose, whose inverse contains the matrix we are interested. And this process is called hermitization. We then performed an analytical inverse. We wrote the inverse in terms of Gaussian integrals and performed a replica trick. And essentially, at this point, we can intervene and perform averages using random matrix theory. And all I wanted to say at this point is that we never did a large N limit, so this result is exact in a sense. And in practice, what this means is that the matrix, rank 1 matrix used here is in fact stable to matrix perturbations under the conditions that I described in so far. And this result can be further generalized by introducing a set of row constraints and column constraints. And in this case, the matrix then is still approximated matrix is still of rank 1. And A hat at this point is proportional to the row and column sums. Let us now provide an interpretation to the matrix A hat. In fact, let us assume that you want to calculate the ranking, but that you don't know the matrix itself, but only the row and column sums. What matrix A hat will you write down? In fact, if you write down an entropy maximization procedure, which introduce row and column constraints, essentially the matrix A hat emerges naturally. Let's see now how the formula applies to fictitious data. We did generate random networks, and using our Erdos-Renyi prescription and scale free with gamma the fitness equal to 2.2. And here we're plotting essentially the average deviation from the ranking value, which is a proxy for how well the model approximates the numerically evaluated ranking using the cut centrality. And what we see is that for a network density, which is equal to P for the case of Erdos-Renyi, the probability at the edge, 0.2, we already have a very good approximation, which means that essentially the ranking can be inferred from only row and column sums. The convergence is lower for the case of scale-free graphs. Nonetheless, at higher densities, the formula works very well. And here we see the difference between scale-free, the blue dots, and Erdos-Renyi for a graph in which the probability of having an edge is 1/2. And we see that for Erdos-Renyi, essentially the formula predicts very well centrality measure. Here we plot the centrality in the rank 1 approximation versus the real one. And in the case of scale-free, there is just more fluctuations, but the formula still works fairly well. We also tested the double constraint formula for in the case of real data sets. Here we use some standard data sets in the subfields that I described before. For instance, in PageRank, we are using a Stanford network for trophic levels, send marks. So that these are very common data sets. And also here, where the graphs and the data sets are ordered in increasing sparseness, what we see is that the formula works fairly well. For instance, in the case of the cut centrality for the Ego Facebook data set, essentially the single constraint and double constraint formula work very well. In the opposite situation where you have very sparse network and fairly small, which is the trophic web of the sent marks ecosystem, the formula does not work as well for the single data set. But if we start to generate using a generative model, an ensemble of food webs with the same statistics, essentially we see that after binning, again, the formula works very well. Also, in the case of the mean first passage time, we see that for two fictitious data sets given by fully weighted random graphs and Erdos Shreni with an average degree of 100, essentially the mean field exact versus the rank one approximation works very well. Moving towards conclusions, what the problems we had described before, the one of the numerical scaling of the matrix inversion is essentially O1, so an incredible speed up, if you do know the row and column sums, and is n squared if you don't. In the case of the second problem, which you might not know the network entirely, all you need to know here is again, only the row and column sums to calculate the formula. In terms of the non-local measures, from essentially these partially explain why it is the case for dense graphs, because the in and out degrees are essentially the row and column sums of the matrix. Regarding the third point, there was the nonlinear generalization. Our averages can be performed also in the case of some nonlinear functions in the matrix A. And without going into more details, there is a formula also for any function of the matrix A if the function is analytic. And for instance, one example is the strata index, in which a similar pattern of network density versus exactness of the formula applies. So in this sense, all the problems that I described before are partially explained by the formula that I just described. The conclusion is then that centrality measures for dense weighted graphs are very well approximated by certain matrices that are rank one and that are determined only by columns and row sums. If you are interested in more information about our works, please see these papers here, and please send me an email in case you have more questions.